And here's your study session for the Unit 1 quiz for pre-calc. Question number 1 is going to be parent graph transformations. And we will be transforming a parabola a bunch of different ways. Number 2 will be function composition. We'll give you a function f of x, a function g of x. And you will need to compose those functions both with an integer value and just function composition itself. 3 will be point slope form with perpendicular lines. And 4 will be laws of exponents and least integer bases. So those are the topics for the quiz. And next we'll do a couple example problems of each. Parent graph transformations. The big idea here is to know what your transformations are. Okay, so we'll use y equals x squared as the parent graph here. Although it wouldn't matter if it was y equals x cubed or 2 to the x or whatever. Okay, but that would be your parent equation. Okay, and then there's various shifts that you can make to that parent equation. All right, you could have a stretch of that parent equation, which would be y equals a times x squared. Keep in mind that if a is greater than 1, it is a vertical stretch. Okay, if a is between 0 and 1, it is a vertical compression. And if a is less than 0, it will reflect about the x-axis. Okay. Moving on, we could have a horizontal shift, which would be y equals x minus h quantity squared. And again, there are specific details here. If it is a minus h, then it will be opposite of what we're thinking and horizontal. So that will move us to the right h units. And if it's a plus h, that will move us left h units. And last, we could also have a vertical shift, which in this case would be x squared plus k. And outside the parentheses is vertical, and it is also as is. So a plus k will be a upward shift. K units. And a minus k will be down k units. And obviously we could have a combination of any three of those all together. So that's what you're looking for tomorrow on the quiz for parent graph transformations. Function composition. Okay, function composition is where we take one function and we actually substitute it into another function. So first we need to have what our functions are. Assuming our functions are f of x equals 4x squared plus 12x and g of x equals the square root of x plus 9, let's perform the following. Let's say it's asking us for f of 2. If it's asking us for f of 2, we would simply substitute a 2 in for all the x values in our function f. So in this case, we would substitute a 2 here and here. And then simplify. So properties of exponents, or excuse me, order of operations says 2 squared is 4. 4 times 4 is 16. 16 plus 24 is 40. Okay. Let's suppose that they were asking us what g of x minus 5 is. In this case, we're going to take the whole expression x minus 5, substitute that into the g equation in place of the x. So we'll be substituting an x minus 5 into that equation. And then simplify when possible. So in this case, we would end up with the square root. See a minus 5 and a plus 9 ends up being x plus 4. Okay? That's just substituting a value or an expression into one function. What if we substitute an entire or a value into both functions, or an actual whole function into another function? Let's take a look at those problems. I'm going to clear some of this here. Okay, let's say we have f of g of 7. That'll make it easy on us. So first things first, we plug 7 into our g equation. So we would plug 7 into that equation, which gives us the square root of 16, which gives us 4. And then we take that answer and plug it into our f equation. So we would have 4 times 4 squared plus 12 times 4. Okay. And let's see here. I'm thinking we're looking at 112 there. But I guess I could always double check. It's just a shot in the dark. Let's see here just to double check. I want to make sure. Look at that. He's back. Okay. Now, that's function composition where we're substituting integer. What if it's just another function? Okay, so again, let me erase. And let's suppose that we have g of f of x. Okay, so I'm going to plug my whole function f into my function g for the x. So I would have 4x squared plus 12x plus 9. Okay, now a lot of people are tempted, oh, I know the square root of 4, it's 2. I know the square root of x squared, it's x. However, when you're taking the square root of a whole expression like this, it's either all or nothing. It's either the square root of the whole thing or nothing. All right, so what we should examine here, first of all, is we don't know the square root of each of these individually. However, maybe we could factor this. Okay, so if you do your box diamond, however you do it, okay, as far as factoring goes, what you're going to end up seeing is that we end up with 2x plus 3 and 2x plus 3. Now, instead of writing those multiplied by itself, we would write that as 2x plus 3 squared. And that's where the cancellation can happen because a square root and a square cancel each other out. So we end up with just 2x plus 3. However, to accommodate the fact that every square root has a positive and negative root, we would have to put this in absolute value bars to satisfy that. Because every absolute value bar also has a positive or negative answer. Okay? Moving on. Point slope form and perpendicular lines. So I'm just going to throw one at you real quick. Let's say we have y equals negative 2/3 x plus 5. And we want to write the equation, an equation in point slope form that is perpendicular to y equals negative 2/3 x plus 5 and passes through negative 3, 7. So if I'm going to do that, first of all, the only thing I need from this is the slope. And I'm looking for perpendicular to that. So I got a opposite and reciprocal. So my slope is going to be 3/2 and positive. And it has to pass through the point negative 3, 7. Point slope form is y minus y1 equals m times x minus x1. So I substitute what I know. So y minus 7 equals 3/2 times x minus negative 3 makes plus 3. So this could be your final answer. You could add the 7 over, so it's y equals form. And that is also acceptable for point slope form. That's what you're looking at on the quiz tomorrow. Last, we have laws of exponents, least integer basis. So let's say we had an expression that needs to be simplified. Something like, let's see here. What if we have, a lot of these look the same. So Okay, and we want to simplify that, all right, so that it has the smallest possible integer base. First of all, what the first step is, we have 3 least integer bases that we use the most, 2, 3, and 5. Remember, 2s are evens, 3s are odds, 5s are 5s. In this case, we have evens. So I'm trying to write 1/8 with a base of 2. Nothing else changes. I'm trying to write 32 with a base of 2. Nothing else changes. So 2 to what power? 2 to what power gives me 1/8? Okay, is what I'm asking myself. In this case, 2 to the third power gives me 8. Negative third power, whoops. 2 to the third power gives me 8. 2 to the negative third would give me 1/8. Here, 2 to what power gives me 32? That'd be 2 to the fifth. If you don't know those, you can use guess and check on your calculator. And then I begin the process of simplifying with properties of exponents. Power of powers. Power of powers says I multiply those. So I end up with 2. Make sure you distribute to the negative 3x plus 6. Over here, same thing. Power of powers means I distribute. So I end up with 2 to the 15 minus 5x. Last simplification here would be that if I have common bases that are being multiplied, I can add their exponents. That's called the product of powers. Okay, so I end up with one integer base, and negative 3x and negative 5x makes negative 8x. 6 and 15 makes 21. That's my simplified answer. Now you look back through those problems plus the problems that I had on the board today in class for extra hints on the quiz. You can also refer to the Moodle. There is a document called Unit 1 Assessment, and there's plenty of problems in there for you to try. There's also a forum on the Moodle that if you do have questions that you can post those to the forum and I will answer them. Good luck, and I will see you tomorrow.